Alright, welcome to Chapter 3. We're about midway through, and what we're going to talk about today is the law of conservation of mass and about classifying matter. So the law of conservation of mass, we are going to come back to this over and over again all the time this year. So when we are looking at the law of conservation of mass, what it states is that mass is neither created nor destroyed in a chemical reaction. It is conserved. That is really important. I'm going to ask you to be able to write that. We're going to say it multiple times in many different forms this year. What does conserved mean? Really, that can also be used as the word transferred, or it can be used as the word converted. So think about it this way. The law of conservation of money states that money is neither created nor destroyed. It is only transferred. If I have $20 and I give each of you $1, I'm $20 poorer. Each of you is $1 richer. Have I destroyed any of that money? No. When it comes to the law of conservation of mass, basically that means that the mass of the reactants, that's what we have at the beginning of the reaction, equals the mass of the products. So it looks kind of like this, and we can write it as a mathematical equation. So in an experiment, 10 grams of red mercury 2 oxide powder is placed in an open flask. It is heated until it is converted to liquid mercury and oxygen gas. The liquid mercury has a mass of 9.26 grams. What is the mass of oxygen formed in the reaction? Don't get nervous by all the words. Just look at it, pick out what you need. So what I'm going to first do is look at what is chemically happening. I have mercury 2 oxide. And it's heated until it's converted. So the word converted, I'm going to use an arrow to liquid mercury and oxygen. So that's my equation. The mass of the reactants, the mercury 2 oxide, should equal the mass of the products, the mercury and the oxygen. So I go back and I look at the math. I've got 10 grams of red mercury 2 oxide. I've got 9.26 grams of liquid mercury, and I'm looking for oxygen, so that's X. The arrow becomes an equal sign, the and becomes a plus sign, and I'm solving for X. So I subtract 9.26, that should be a 6. And I believe I'm going to get 0.74 grams of oxygen. And that's it. So that's the law of conservation of mass for now. We'll add on to that later on. So what I want you to do is I want you to work this one, and then check it with your peers tomorrow in class. And then I want you to work this one. So the classification of matter. This is another topic that we're going to be talking about in Chapter 3. When we classify matter, we classify it as either a mixture or as a substance. A mixture is going to be something that is mixed together, like Chex Mix, lemonade, gasoline, still, milk, blood, dirt, things like that. A pure substance, on the other hand, is something that's going to be on the periodic table, or it's going to be a compound that I can only break down through chemical means. So this chart's going to be helpful. Chemical changes over here, physical changes over here. Alright, so a mixture, like I said earlier, it's a combination of 2 or more pure substances in which each pure substance retains its individual chemical properties. So you can either have homogeneous mixtures in which you have a constant composition throughout, or you can have other kinds of mixtures, which are heterogeneous mixtures. A homogeneous mixture can also be called a solution. And then you have the heterogeneous mixtures, which is where the individual substances remain distinct. So if you think about the prefix, homo means the same, hetero means different. So if it's a homogeneous mixture, it is going to be constant throughout. Think about things that could be a homogeneous mixture. Milk, butter, salt water, pure salt water, not like the ocean. A heterogeneous mixture could be Chex Mix, it could be a salad, it could be sweet tea with ice in it if the sugar has settled out, things like that. So, air is typically going to be a solution. So solutions are things that are going to be homogeneous because they are going to be completely uniform throughout. Same composition the whole way through. Now, a pure substance is going to be made up of matter. Everything is made up of matter, but a substance is going to be made up of matter that has a uniform and unchanging composition. So what that means is that a substance is something like an element, which is gold. All you got in gold is gold. Okay? If it is a compound, which is another type of substance, that's like water. Its formula is H2O. So you've got 2 hydrogen atoms for every 1 oxygen atom. And that's always going to be true. It's a uniform and unchanging composition. So an element is a pure substance like gold that, as I mentioned earlier, it cannot be separated into anything. That's an interesting star. It cannot be separated into anything simpler by physical or chemical means. We'll talk about nuclear at the end of the school year. There are 92 naturally occurring elements on Earth. Uranium is the last naturally occurring element. And each element has a unique name and symbol. They are on the periodic table of elements. So, you've got a grid of horizontal rows called periods and vertical columns called groups, and we'll talk about that a lot more in chapter 5 and 6. Compounds are 2 or more elements combined chemically. Chemically means that I can't just pull them apart. I have to undergo some sort of chemical process, change the odor, change the temperature, change the chemical makeup of it to pull them apart. So most everything exists in the world as compounds. You are made up of lots of compounds. I am made up of lots of compounds. Your cell phone is made up of lots of compounds. Table salt, NaCl, which is sodium chloride. You can find those on the periodic table. And water, H2O, dihydrogen monoxide, are compounds. And an element can't be separated, while a compound can be broken down. So if you look at this, if I take water and I put it under electrolysis, which this is called hydrolysis, I'm going to be able to take water and separate the oxygen from the hydrogen. That's separating a compound through chemical means because I have applied electricity. So the properties of an element are different than the properties of the compound. So even though hydrogen is flammable and oxygen is flammable on their own, together, when you put them together as water, water is not flammable. So, that's how we classify states of matter. So now we're going to do a couple examples. So, remember, go back to this. Now look at this. If I look at air, if I'm talking about the air outside this classroom right now, it's actually going to end up being a mixture. And then we can argue about whether it's homogeneous or whether it's heterogeneous. It's homogeneous if it's uniform throughout. It's heterogeneous if it's not. I'm going to say the air in Nashville is heterogeneous because in certain areas you're going to have more oxygen. In other areas you're going to have more pollution from cars. However, if I said air on the International Space Station, it would be homogeneous because it's always run through a filter. But it's definitely a mixture, and I'm going to make the argument that it's heterogeneous. Water. If it's just water, what is water? It is a substance because it is always going to be a compound, because it's always going to be, it is always going to be 2 parts hydrogen, 1 part oxygen. Gold. I can find that on the periodic table. So that means it has to be a pure substance, and it has to be an element. Alright, salad. Can I take a salad apart with my bare hands? Yes, that means I can separate it through physical means, which means it is a mixture. And since I can pull it apart, it is going to be heterogeneous. Because, you know, I have like croutons and tomatoes and carrots and cheese and all the other weird things you put into a salad. And then sweet tea. It's definitely going to be a mixture because it's not always a uniform composition. And I can pull it apart through physical means. I'm going to go with the fact that since the sugar is distributed evenly throughout most of the time, like if you actually make sweet tea, not like get unsweet tea at the restaurant and stir the sugar in, but if I've actually made sweet tea, then I'm going to go with the fact that it's going to have uniform sugar throughout, and so it's going to be a homogeneous mixture. So hopefully that helps. If you've got any questions, make sure you read this section of Chapter 3 in your book. Thanks so much for your attention.